Okay, so now Professor Kunihito will present to us about inflationary scenario, quintessence, cosmological landscape, and the swampland.
Thank you very much for giving me opportunity to talk here. And today I'd like to tell you about the digital compactification and dark energy model and some kind of this on the topic of the string cosmology. This work is collaborated with some of the Japanese guys, but so the now my interesting work is based on the cosmology and black hole physics on the basis of string theory, because string theory is one of the candidates at present in the unified theory. But of course, this is very passionate and interesting theory, but a lot of problems still may remain, unfortunately. But the string theory so relate not only the particle physics, but also general relativity and cosmology. Of course, even if we consider the rate time cosmology. But for instance, today, so I'd like to focus on the some cosmological model. Then the topic of the string theory related to the cosmology is how to produce information involved in the early universe, the expansion of our universe, and some kind of modular stabilization. I will briefly a little bit later about that, because string theory requires the space-time to be higher dimensional, more than 4 dimensional. But the real universe, we can only so observe the only 4 dimensional space-time. Then so remaining so internal space extra dimension, where is that? So we need to fix the scale of extra dimension. This is modular stabilization problem. How to resolve it in the context of string theory. And so how to produce not only information in the Halley universe, but also the late time accelerating expansion of universe. If we so want to resolve some of the problem, origin of the dark energy, accelerating expansion of universe on the basis of string theory, so we are very happy. Not only some of the cosmologists, but also the particle physicists. This is my opinion. But unfortunately, I said again, so string theory does not currently provide a satisfactory model, unfortunately, of the model of not only the early universe, but also the late time universe. So today, my talk is focused on the problem of two kind of things. This first one is modular stabilization problem. The other ones I will briefly comment about later, how to produce the digital space accelerating expansion universe. First, so I will briefly comment about the modular stabilization. So string theory or the unified theory normally so requires the space-time to be higher dimensional, more than 4D space-time. In order to obtain the 4D universe, we need to so construct a compactification. So we need to conceal the extra dimension. We cannot see at present the space of the extra dimension. So how to measure, how to analyze the dynamics of extra dimension? I will briefly comment about that. The compactification gives rise to various new problems. So modular stabilization problem. But now very simple models. Everybody here knows about the philosophy of Karuza-Klein model. It's a very simple model. So this is a initially 5D model. Of course, the more than 5D, it's okay. So in the very early universe, for instance, we could observe that 4 space, higher dimensional space, more than 5. But at some stages, some mechanism did work. about the some shrinking, collapsing, so the scale by extra dimension, while the 4D universe expands. How to do that? So it's not so easy for us to do exactly in this unified theory, including a string theory like this one. This is a real modular stabilization problem. We can fix the scale by extra dimension, very, very tiny scale. We cannot observe at all. On the other hand, 4D, so again, so seeing the expanding universe, we need to fix the moduli. We need to fix the scale of extra dimension, which is so-called moduli stabilization problem, to obtain the realistic cosmological model at all. So I can show you the very simplest model of the compactification, Karuza-Klein compactification model. And this is the line element of the higher D. Okay, so the GM and M is from 0 to the D minus 1. This is the line element, for instance, the 4-dimensional universe. This is the metric of extra dimension in front of here. So this is scale of extra dimension. Okay. Of course, we can consider the much more some complicated extra dimension model, but here, so I will comment about the very simple Karuza-Klein model. And if, for instance, consider very simple Lagrangian, including not only the gravity, rich scalar with respect to the metric higher D, GMN, but also there's some matter field. So, for instance, field strength, cosmological constant, anything you want. Substituting the line element into the Lagrangian of the original higher dimension space-time, we can calculate easily like this one. Of course, so integrate the internal space out in this the action, large D-dimensional action. Then we can write down some the 4D effective action like this one. This is the original higher D gravitational constant, and this is a 4D gravitational constant, which is related here. So 4D gravitational constant is proportional to the inverse of the extra volume of the extra dimension. If we consider large volume of extra dimension, so 4D gravitational constant much more weaker. And this is a rich scalar with respect to the 4D metric, like this one. Okay. And this is quite important. So Lagrangian coming from the scale of extra dimension. Okay. This is this B denotes the scale of extra dimension. But this is here, phi is written by the scale of extra dimension. It's normalized like D here. This is canonical scalar field model. Okay. And this is potential of the scalar field phi, but potential means the moduli field B. This is scale of extra dimension, which is so-called moduli. But the moduli potential coupled to the original matter field in the higher D, and this is coming from the curvature of extra dimension. Okay, if we consider D-dimensional sphere, we can write like this one. Okay, which coupled to the moduli. So the power of the moduli depends on the matter field. Okay, so field strength, cosmological constant, and the curvature scale, curvature of the extra dimension. So I'd like to go back to the issues, how to analyze the dynamics of extra dimension. The answer is like this one. We can check the scale of the scar field phi. And important things, how to fix the scale of moduli. Okay, you can construct the potential of the moduli, like the global minima and the local minima. But unfortunately, not so easy to produce the minimum of the moduli. Long time ago, many people sort of discussed about that. Runaway type potential of the modular field will be produced after compactification. So if we simply write down some of the modular potential, we can easily obtain like this one. So that this is runaway type, so that we cannot easily fix the scale of extra dimension. And in order to stabilize the scale of extra dimension, we can put it in some of the matter field and the quantum correction and cosmological constant. So this is ideal situation of the fixing moduli like this one. Of course, the global minima okay, but this quite difficult to produce the global minima. But now, this is the second ideal case is a metastable moduli field. For instance, the stabilization moduli field strengths given by the field strengths and the quantum correction. Then we can get the fixing model of extra dimension. But the role of some matter field about the fixing moduli like this one. So if we put it in, so if we consider the field strengths, gauge field strengths in the background, this contribution like this one prevent the internal space from collapsing, because if the field strengths penetrate internal space, so if we force to some collapsing the extra dimension then that contribution of field strengths prevent the internal space from collapsing. Good. On the other hand, if we put in the background about this cosmological constant normally is a repulsive force, then this contribution will be expanding of the internal space, like this one. On the other hand, the curvature, so the internal space is very important to consider extra dimension. If we assume extra dimension will be a sphere, okay, positive curvature, that contribution makes the internal space shrinking. On the other hand, if we consider some of the negative curvature internal space, so it's this is a contribution is the same as this cosmological constant, expanding the internal space. So if we go back to some of the potential picture, like this one, this contribution coming from the field strengths, okay? The other one is that this is a contribution coming from the curvature of the internal space, for instance, a sphere. And finally, this line is given by the cosmological constant and some the quantum correction. This is very important. Three kinds of things we can produce the metastable, and this is a positive potential, positive energy around the local minima of the modular potential. This is important. The reason why I will comment about later. This is first one is a modular stabilization problem. The second one is how to produce the accelerating expansion universe given by on the basis of string theory. There is no go theorem, unfortunately. So the very big guy, so Mardasana, he discussed the some the no go theorem coming from the compactification in the string theory or the higher dimensional gravity theory. They assume a lot of assumption. For instance, that there is no negative potential. There is no higher curvature correction in the string theory. There is no fundamental object like the D brane and the orientifold brane in the string theory. There is no singularity in the internal space, but very natural. Some assumption in the higher D. But if we assume all of things, it's very difficult to produce the accelerating expansion of a 4D universe. And this is our theorem, very famous. As Drexel said about it's not easy to realize, and Dojita space in the string theory. But how to produce some the Dojita space on the effective theory of the string theory? The answer is the important thing is first one is we can produce the minima of the potential. And positive energy will be required around the minima of the potential. Okay, the two kinds of things, but very difficult. The reason why. So I will go back to some of the very simple Einstein equation, including the scalar field. This is the same or almost same situation. I will go back to some of the initial setup about this compactification. That Lagrangian, so previously, so you can remind this. Sorry, this one, gravity and the scalar field and the potential. This is situation. Okay, so let's consider some Einstein equation things. Okay, this is of course this is put it in the original cosmological constant, but T mu is include the scalar field only. Then everybody here knows, so we can so easily write down the Einstein equation. But if we can construct for this space and the potential of the scalar field like this. Okay, so around here, so probably the scalar field kinetic term will be kinetic term of scalar field will be 0. Okay, because this is around here, so fixing. On the other hand, the potential of the scalar field will be positive. Then how to consider how to construct this Einstein equation? This is a neglecting term. This is a dropout, and only here. But the potential will be positive. Then we can get like this one, like this. Okay. If we neglected, of course, get rid of the original cosmological constant. This is it's the same contribution of the cosmological constant given by the scalar field with any minima. Okay, this is so-called an effective cosmological constant. I'd like to stress that if we realize the shape of the moduli potential like this, we can fix the scale of extra dimension phi and giving the positive cosmological constant in 4D. This is a very ideal situation in the effective theory, but very difficult because it's naive considering about this the Einstein equation. So we can never mind about any matter field, for instance, then vacuum background. Then the Einstein equation like this very very simple. So reach scale equal to zero, and it's divided by two parts for the reach scale plus the scale reach scale of extra dimension equal to zero. Then we can immediately understand the situation if we construct the 4D digital space. This is positive curvature. Then extra dimension. Curvature of extra dimension must be the negative hyperbolic space given by Townsend and Wolfram. On the other hand, it's easy to realize that some the compact sphere extra dimension. Then on the other hand, the 4D space is negative curvature, ADS background. This is some kind of point Rubin compactification in 1980s, very famous. Of course, we can consider the other things, putting in scale field, matter field, but so the property of this situation a little bit modified only. Then I'd like to stress that normally we can consider digital space in 4D, then so the internal space so wanted to be some negative uh, curvature scale like this one, unfortunately. But there is a quite famous for realizing the digital space coming from the string theory in the 25 years ago, almost 25 years ago, given by the Karlsruhe in the Trivedi, so-called KKLT model. Somebody already know about this one. They consider that a lot of the matter field, but they consider the contribution of the fundamental object of the energy of the brain. Okay. Simple compactification, including a quantum correction, they realize, of course, the minima of the moduli like this one, but unfortunately, negative potential around the minima of the potential. But they put in the contribution positive energy coming from the D brain, lifting up like this one, and they succeeded the construction of the zeta minima. Okay. This is a some kind of famous model. Then, so people thought about okay, so this is a finished discussion is finished about the some construct digital compactification on the string theory. But so the after that, so around the 2018, somebody so the Ori Buffers proposed the other proposal about the digital compactification. I will show you later. The basic concept of the swampland, firstly discussed by the common buffer. The other string theories give rise to a huge number of the vacuum on the background, unfortunately. So simple, sorry, complicated some the string model like this one number of vacuum tend to the like this one, huge number of this some very, very huge number of the vacuum like this one. So people thought about that there is no predictability on the basis of string theory. How to select the real vacuum in the string theory? We need the criteria of the conjecture. So to specify the unique model and this, so give rise to the real universe on the basis of string theory. And the reason why so huge number of the vacuum were produced, the answer, one of the answer is like this one. Of course, a lot of the effective theory will be produced, but not all consistent looks. So looking at effective field theory can couple consistently to gravity with UV compression. Of course, we can construct, okay, so we can get for the effective theory, it's perfect. But what is correct? Because I if consider sort of coupled to the gravity, there is just not consistent with the quantum theory of gravity. This is the point. Then we can get rid of the wrong type of the vacuum was theory. So uh, in the background. So perfect so called a set of all effective field theory, which is ultimately inconsistent with string theory as a swampland. We cannot live in the swampland. Okay. If we have some the correct vacuum, we can call the string landscape. But how to measure? How to criteria? So get rid of all of the wrong type of the effective field theory. We need to propose the criteria measure of the swampland. This one. Then of course, I collaborated with Carlos about some of the issues of boson stars. Okay, so this time this talk so different things in the viewpoint of the cosmology given by Dojita space. There is Dojita conjecture discussed by Ogri Bapa. Okay, this is first of all this is the result of the Dojita conjecture. This one, if we consider the rich scalar coupled with scalar field on the 4D theory, then if we assume positive energy, positive potential of the scalar field, there is lower bound of the relative. So derivative B over B is larger than constant, order one constant in the unit of Planck's mass. The C is, of course, the order one parameter, which depends on the number of extra dimension of the total dimension like this. So this is motivated by the observation, by some of the dark energy or inflation. But so please remind about this type of the equation. Okay, so that if the theory does not satisfy this criteria, what's the problem? What comes from this type of some equation? The theory is not consistent with the quotient motion, for instance, Einstein equation, the scalar field equation, and energy condition, strong or null energy condition. But so I'd like to go back to the KKLT model like this one. Okay, so we can get digital vacuum like this one, produce the very, very natural potential like this one. However, the potential like this one has produced the metastable over there like this minima, but here derivative b equal to 0. Okay, so doesn't satisfy this one because this is 0. 0 over b is 0, not larger than order 1 constant. Then these people stress that KKOT ideal model will be swampland, which is not consistent with the quantum gravity. This one, okay, so the potential quantum gravity has local or global minima if the potential energy mass at minimum is positive, like this one. So they stress that the stable Parkin string theory will give only ADS, not the DS. So again, I said because this is like this one here is a derivative equal to 0. But of course, the B is larger than 0, but like this one, so they didn't satisfy anyway anymore. So There, there is no digital vacuum in string 311. But a lot of people thought about the other modification of some of the criteria. The 2019, some conference, Rinde, KKLT model, Rinde, asked about some question, okay? So the derivative V over B, the newest observation data implies 0.09. Now, probably it's zero point 0.5. Now, is 10 to minus 2 order 1. So the answer will come about 10 to minus 10 is not certainly order 1. This is not the answer question. So Linda was very angry in in the workshop. So this is not answer, satisfied answer. The reason why this complicated situation because the going back to the originally assumption of the swampland digital conjecture and novel theorem of the digital compactification given by the Mardasana. They assume like this one, all of things. No alpha prime correction means a higher there is no higher curvature correction in the effective theory of a string. No D-brane or plane. This is fundamental object in string theory. No singularity in the internal space, of course, 4D space. All matter satisfies strong and neural energy condition. And this is some given by the Mardasana assumption. The Ogre offers much more further assumption like this one. So the velocity of the moduli is set to 0 all the time. Okay. On the other hand, KKLT model, they consider some kind of the fundamental object like this orient for plane and D brane. Then if we discuss about how to produce the 4D digital space, like the conjecture, we have to construct, including these fundamental objects and some proposed all of some of the things. My understanding is that the KKLT construction contains normal gradients in validating the normal theorem. If we propose a new normal theory, including these objects, it's fine, but there is no inclusion about fundamental object of the string theory. Going back to the conjecture like this one, derivative B over B is larger than order 1 constant. They assume there are some point like this one, so the derivative of the B, B is larger than 1, 0, and some kind of some satisfied some energy condition, stronger neural energy condition. And this one, derivative of the some scarf field equal to 0 all the time. But this is, I think, my understanding is very problematic. Of course, inflationary scenario that we assume that some slow roll condition. The derivative of the time derivative of the scale field over the potential is nearly 0. It's marginally okay, but on the other hand, the quintessence dark energy models, we don't need to consider the slow roll condition. But the digital conjecture, they use also use some higher D equation motion, of course, lower D equation motion with some energy condition. Then can get some digital conjecture. This is some detail of the model like this one. they assume like this higher D line element. Okay, so this is some the 4D times extra dimension. Okay, this is tau. Tau is a moduli in front of the some metric of the internal space. This is a moduli. Scale this scale field denotes the scale of extra dimension. Okay, and volume moduli so called. The other moduli, so we can specify the phi, large phi. On the other hand, we also consider strong energy condition corresponding to RTT is larger than zero, and higher D or lower D Einstein equation, of course, the scale field equation coming from the moduli. First, now sort of substituting a line element into some rich tensor. Of course, that this is some the equation, and using the Einstein equation coming from the line element like this one, and some the adding some lower dimensions Einstein equation, you can get like this one. This one, very very simple. Okay, but this one, this is very important contribution coming from the tau dot square. But Augury buffer, originally digital conjecture, they neglect the contribution like this one. Of course, we drop this term. Derivative b over b is some of the order one constant in the unit of the Planck mass. This is number of the extra dimension, the total space, and this is a number of extra dimension. While the alpha depend on the like this one, the number of extra dimension and the total space like this. So, okay, if we assume the thorough condition, this one, the relation going back to here, original digital conjecture. But if we consider some dark energy model, we don't need to neglect the contribution of this one. Okay, how much time do I have? 20 minutes? Okay. Here we try to apply the dark energy model. Of course, inflationary scenario, it's same as like this Augury buffer because normally we specified imposed some the thorough condition, then going back to some the digital conjecture. But if we remain the term, this one more term, what's happened to modify the result on the cosmology? Sorry. Dark energy, of course, originally named by the Michael Turner in 1999 because 1998 there was some of the observational facts given by some of the Paramatta or Adam Rees, the accelerating universe. Then, cosmological observation shows the current accelerating expansion of universe is caused by dark energy. But we assume that lambda CDM model of cosmology is correct, and dark energy contributes around 70%. Okay? But if we consider some of the scale field on the expanding universe, so what's happened? What's the role of the scale field? In 1980s, Peebles has already discussed in detail. Okay, but that in those days, this is a toy model because there is no observational fact about the accelerating expansion of our universe. unfortunately. But this is a very, very sort of important work about some of the dynamical scale field on the expanding universe. So Einstein equation going back to with the dark energy like this one, if the phi equal constant, dark energy of course is that so not dynamical, which may so-called cosmological constant, because this is a these are zero and the constant potential energy, which it's exactly same as the cosmological constant. But now, so observation of facts force to the changing mind about some of the cosmological constant because change dark energy depends on time. If so, the dark energy is given by the scale field. We can seriously consider the scale field like this one. So, one of the such model is quintessence given by the Paul Steinhardt, because the equation of state W is P over rho is like this one. This is some time dependent. This is a new type of the scale field in those days in 1999. On the other hand, cosmological constant, as you know, this W equal to -1. Okay, so this is drop off. This is a B minus B over B is -1. But it's very difficult for us to realize that some the very tiny energy, milli-electron volt in our universe. How to realize that? One of very naive model is like this one, runaway type. Okay, this is some kind of the exponential potential is much better because we can solve the equation motion about scale field. Firstly, in the inflationary scenario, somebody solved some exponential potential, and we can get some of the accelerating expansion model. But in 1990s, so Watrich discussed about the toy model. Of course, the much more the higher D model. We can set the scale potential like this one, exponential. This is some of the slope of the potential like this one. This is a lambda is constant and positive value. So we can analytically solve like this one. So the tau, not only tau, but also the scale factor Hubble and all of things so that we can get the exact dynamics. On the other hand, the very important things, tau dot square over V equals constant. Very easily because put it in like this one. And the tau dot is also the T2 minus 2, or like this one, T2 minus 2. So the tau dot square over the B equals constant. Then, like this one, how to contribute the model like this one. If we consider the exponential potential as some quintessence, and the tau dot square over B is some constant value. How to change the value? What doesn't change? Of course, it depends on type of model, of course. But it's very nice situation considering exponential potential because string theories consider the Dojita conjecture. On the other hand, for the astrophysical physicists or cosmologists consider solving the 4D Einstein equation with not only scale field but also radiation and the other matter field, numerically, of course. We never solved analytically all of the matter field in the 4D universe. So they said, like this one. So lambda is the slope of the potential. is less than 0.85 in using all current observation data, baryon or acoustic oscillation, or the supernova data, including lambda is less than 0.6. Okay, on the other hand, Dojita conjecture denotes lambda is must be larger than root, so 2 to 1 over 2. This is some kind of the tension between the 4D observational cosmologies and the string theories. Of course, string theories didn't consider any matter field of the radiation of the dark matter or things. But very curious things, the cosmologists so frequently referred the Dojita conjecture. Okay, lambda must be the 2 to 1 over 2. But some results consistent with the observational data is less than 0.8 or 0.6. This is the tension. I don't think so because we have a lot of contribution. So not only some of the matter field, but also the assumption like this one. They neglect the contribution with some of the velocity of scalar field. Of course, in quintessence models, a lot of people assume slow roll condition, but we don't need to so every time impose the slow roll condition. If we can seriously consider the contribution coming from the velocity of the moduli like this, okay? Slowing down, but we cannot neglect the contribution of velocity. What's happened? You can check like this one. Lambda never larger than 2 to 1 over 2. For instance, if we consider the 10-dimensional string theory and the 6-dimensional compactification, this is around the region of lambda 0.5 or 6 and larger than the 0.6, the less than like the 90. Okay, this is I think the quite marginal about this one. Okay, or the 11D also lambda is larger than 0.5 and is less than 20. Okay, not must be larger than 2 to 1 over 2. Okay, so the point is that we don't need to specify or impose the slow roll condition, at least in the quintessence model. Okay, I think there is mild tension on the Dojita criteria. Okay, if we consider the contribution of velocity of. Okay, so I'd like to conclude the telling again. So there is a Dojita criteria on the basis of string theories, but very simple model, only the gravity and scale field, but very, very so simple equation criteria. But they assume velocity of scale field is 0. Then recent also cosmological observation never saw the consistent with some of the Dojita conjecture, unfortunately, at rate time acceleration. So if I wanted to modify some of the conjecture like this one, very simple. One time, seriously consider contribution coming from the velocity of a scale field. Then we can get some of the modification like this one. For instance, we'd like to add some of the one more comment. We have found the contribution of the tau dot square over b depend on the dimension like this one. For instance, if we start the 5D, the tau dot square over B is zero point 0.9, not less than 1, I think. Of course, 10 or 11 dimension is much more so the much less than the 5D case, but we can seriously consider about the contribution of the velocity of the scalar field. Then, as you like to stress, we can modify at least the velocity of the scale, modify the conjecture. Yeah, of course, this is I think that this is a very seriously contribution about some of the the criteria about this whole 5 or 6. On the other hand, we consider that the other neural energy condition, it's almost same result. Okay, so it's okay. Okay, I will stop here. So thank you so much. Appreciate it.
Okay, so do we have any questions?
Sorry. No, no, no.
Because the question was about the compactification, right?
Well, thank you very much, first
Yes,
of
yes.
all, Kunihito. I mean,
Yeah.
you gave a very nice overview about many
Yes.
topics and the difficulty about getting the sitter from a fundamental theory like string theory.
Yes.
And this has been a very important problem. And some of these solutions, like the KKLT, they are, to me, a bit mysterious because they invoke things like Gaussian condensation and quantum effects that no one really knows very well how they come about, besides orientifold planes, D-branes. So it's very complicated. I worked in this long ago,
Mhm.
but as far as I understood, so you told us something interesting, which is even the simple runaway potentials that you get from simple
Mhm.
compactifications, like this exponential potential, it could perhaps explain observations, right? With the right set of parameters. So you never get like a minimum with a positive energy. It's running, but if it goes with the appropriate parameters, perhaps it could fit observations, right?
Mhm. Mhm.
So, and then what was confusing me was you are now describing this table where you have here the velocity of the scalar field
Mhm. Mhm.
and you have the number of dimensions, and you're telling us that this velocity is somehow fixed, if I understand correctly. And I was wondering how much this is model specific, meaning I can go from 5 to 4 in a torus, but from 6 to 4, I can go in a 2 torus, well, a torus, 2U1 or in a S2. From 7 to 4, I can go in many different ways. So those numbers that are there, are they model specific? So you chose a particular compactification, or are they generic? So that was my question.
Ah, okay, so of course, this is not generic potential. Of course, I can specify some of the exponential type of potential because we can easily solve the equation motion analytically. Okay, but so on the other hand, there is some we have to propose not only proposing some criteria but also comparing some observation of the cosmology, observation data of cosmology. Then, first of all, of course, if we consider numerically solve the equation motion in a much more complicated quintessence model, of course, but what type of the potential is much better? Nobody knows about this, at least for quintessence, of course. Then it, we can check the first step. First step, okay, the exponential type of potential because it's quite reasonable. Of course, this is runaway type. They're very simple. Yeah. So generic, it looks like generic property of the some runaway type described by the exponential. It's much better, I think. Of course, so we can consider the other some a lot of some two kind of scale fields, three kind of scale fields. It's okay, but probably my understanding is not so different. But a property about this, if we add some the extra scale field, 1 or 2, 3, 4, 5, it's almost same, I think. Tiny percentage will be modified, but nobody so will be so the uh, attention much more. We consider the scale field as a lot of scale field because somebody, of course, considers the multi-scale field, digital conjecture. Okay, but that never drastically changing the result in the quintessence model. Then so we decided simple one single scale model, and so we can easily solve the equation motion and tau dot square over b. You question a lot of things, but so analytically computed contribution coming from this one. This one. But originally, I assumed we can get the contribution is compensated is here. Then this is derivative b equal to 0. We are happy, but never. Can you understand? Because first motivation of the modification of the Dojite conjecture, I wanted to realize the derivative b over b equal to 0. Then, so the KKLT will be recovered, not swampland, okay, so landscape. The point is that this is constant. Then this is the contribution will be compensated. This one that equal to 0. We are happy, but not so easy, of course, as you know. But the one candidate is the exponential type potential. This is a constant value, but they depend on some of the constant value in front of this one. Not so easy, unfortunately. So okay? So the answer of your question is not generic type of potential, as you know, of course. But this is the exponential type is natural potential after compactified extra dimension, as you know that. Okay, so next, so I will comment about the next step. The modification of the digital conjecture will be some the other fundamental object like D plane or orient fault plane, which approaches to the real string theory model. Then nobody's touched some of the criteria or the no theorem about this one. Then so the real compensating, comparing with the KKLT model. This is a simple, very, very toy model. Yeah. But okay, so after that, so the discuss was it.
So, is there any further questions? Well, I have a very quick final question,
Yeah,
which
sure, of
is
course.
about the quintessential model. You showed that the equation of states. Well, the equation of states, the W parameter depends on the
This one? Yeah.
yes,
Uh-huh.
that formula. So I was wondering because in lambda CDM we think about the universe as epochs. So there was the radiation dominated epoch, there was the matter dominated, and the dark energy dominated. Is this a natural way to make to model the transition of different epochs to make this W parameter run over time?
The answer is for the cosmologists. So of course, try to explain naturally. So first of the radiation dominate, the other one the matter dominate. The finally, so there's of course that dark energy dominate the model. Of course, we can choose so numerically, okay, a lot of parameter was some of the dynamics. No problem at all, I think. But the point is that so the what kind of potential we should choose. Not only the observation data consistent with observation data, but also some of the fundamental model, such as the supergravity of string theory. If we put it in some potential, very complicated potential, but what is the origin? Yeah.
Okay, so let's thank Professor Kunihito.
Thank you so much, Christian. Thank you.
And that's it for today. So good evening, everyone.